Good afternoon, everybody. We are starting here in this crazy week right before spring break. Hope you guys are hanging in there. I barely am, but we will make it a few more days. So here is another pod lecture on chapter 14, section 14.7. You can see here it's called polyprotic acids. And polyprotic acids just mean that you have acids here that have more than one hydrogen. If they have more than one hydrogen, they are able to donate more than one proton. So you can see this has 2 hydrogens, sulfuric acid, phosphoric acid, it has 3, and carbonate acid has 2. So it has different dissociation constants and different Ka's is what I'm actually saying. So in my first reaction here, if I'm going to take my carbonate acid, and this first reaction I'll write it with water so you can see it both ways again, just as another form of review. We know that all acids are aqueous and they're going to dissociate in water. This is a weak acid, so it's going to dissociate some, but not as much as a strong acid. So I'm going to get my hydronium ion, and only one hydrogen is going to be able to be donated at a time. So you can see that I have my carbonate ion, hydrogen carbonate ion here. So here I have my acid, so then this makes it a conjugate base. Well, in the second equation, you're going to see that this conjugate base that I have over here, my hydrogen carbonate ion, is now going to become the acid. And this one, I won't write the water. We understand that it's there. And so I'm going to get this to dissociate into my hydrogen ion concentration and my carbonate ion. So in both cases, it doesn't matter, again, which way you write it. Whether you add the water, you get the hydronium ion, or where you do the shortcut and you just have the hydrogen ion, it means the same thing. In this first equation, it's called, I have a Ka1. You know you would have an equilibrium constant, but this is in the first dissociation. And then here, because I have more hydrogens to able to contribute, this would be my Ka2. Now, do they provide the same amount of ions donating? And the answer is no. Acids easily lose the first hydrogen ion, but the loss of the second and the third are more difficult due to the negative charge on the acid increasing. So because of this negative charge right here, it makes it a little bit more difficult if you think about the affiliation that water is going to have for that. It becomes more difficult to remove the positively charged proton. And again, we're talking about the hydrogen ion. So in a nutshell, all this is saying is that you are going to have less dissociation, and that should make sense to you if I have a weaker acid. Now, this is all true, except for if sulfuric acid. So you can see that sulfuric acid. If you remember my little jumpiness yesterday with the conductivity apparatus, the thing with the light bulbs, you remember the first time I put it in there, yes, it lit up the light bulbs because it was a very, very strong acid. And then you saw me pour it into water, and I jumped a little when I put it into the conductivity apparatus. And that's because in the second step, this hydrogen ion still significantly contributes in the second step. And so there was still a lot of ions associating, so there was a lot of current flowing through there. Not only was the beaker warm, but it also created more of a spark. And so the second dissociation of sulfuric acid is really the only acid that does greatly contribute. So we wouldn't say that this is true for sulfuric, but we can say this is true for typical weak acids, that the Ka1 is going to be greater than Ka2, greater than Ka3. Okay, that's that section. So we're going to do one more section before we end here, since this has only been 4 minutes. Hang in there. So we're talking about acid-base property of salts. So salts having cations, so I'm thinking cations and thinking something that has a positive charge, of strong bases, and anions of strong acids have no effect, this should say no, have no effect on the hydrogen ion concentration. So let's decipher this a little bit. So what this is saying is that if I have a positive cation of a strong base or a anion of a strong acid, my pH is basically going to stay the same. So for conjugate base of strong acids, it's going to equal neutral solutions. And we'll talk about that in just a second. And conjugate acid of bases equal neutral solutions. All right, so it sounds like a lot of things that we need to decipher. Says salts that have alkali and alkali cations have no effect on pH of aqueous solutions. So in the past, we talked about these alkaline, we called them spectator ions. So here they're spectators again. They have no effect on that pH of the aqueous solutions. We've talked about how it's really important to have us there. We all want to be there cheering, and we're in the crowd. We don't have effect of the game, but we're still important in the whole scheme of things. So here's an example. So if we take a look at this, you should recognize that HCl is a strong acid. It's going to dissociate into the hydrogen ion and the chlorine ion. And so this is going to be a very strong acid, and this is going to be its conjugate base, and it's going to dissociate 100%. Well, here is a strong base, and I have the same situation. Well, if I take a look at NaCl, all right, we know that that is a salt, and if it's going to break apart, which it can, I would have my sodium ion plus my chlorine ion, and then what's happened here, if my sodium is an alkali metal, so it has no effect on it, I'm really taking a look at just my chlorine ion. So if I rewrite that, I know my chlorine ion -1 there, I know that I have it in water, and what actually happens here is there is no reaction. It doesn't happen. It cannot, this is not strong enough here to pull off that hydrogen as you saw in some of the other equations that we're writing. And so because of this, it's not able to affect the pH. So any of these ions, like chloride ion or my nitrate ion, because that comes from a strong acid, this also comes from a strong acid. Sulfuric acid, here is the anion from that. All of these have no effect on our pH because they are such weak, or they are such strong conjugate bases. I'm sorry, we have a strong acid, so it'll be a weak conjugate base. They're so weak that they cannot pull that hydrogen ion off of there. All right, so if we continue on, for any weak acids, you can see that we can take our Ka times our Kb, and we're going to end up with the constant, equilibrium constant for water. And if you remember, that equilibrium constant is 1.0 times 10 to the -14th. And so whatever these Kas are multiplied together is going to equal this. And taking a look at our Kas, we'll be able to tell if we have weak acids and weak bases or vice versa. So how does this happen? So I have a salt containing a strong conjugate base of a weak acid will form basic solutions. All right, so if we take a look at NaF in solution. So here is what our solution is going to be, is sodium fluoride. Well, if I take a look at the parts that I have here, I have a sodium ion, I'm going to have a fluoride ion, and I'm going to have some water. Well, if I continue to take a look at this, this should have no properties at all. It's not going to affect my pH. I have that spectator ion again. This is going to be a conjugate base of a weak acid. Well, you might say to yourself, how do I know that? Well, if I think about what the acid is going to be, it's going to be HF. It's going to be hydrofluoric acid. I know that that's a weak acid. So then this is going to be a strong conjugate base. And then I have water. So my essential equation then is going to be my, sorry, that -1 is always a little crazy there. Must be how I'm holding my pen. So my fluoride ion is going to be in my water solution because it does say that I am making a salt water solution. And I'm trying to get to equilibrium. I'm going to get this weak acid that I just mentioned, hydrofluoric acid, and I'm going to get the OH properties left over. So when I take a look at this, I again have a salt containing a strong conjugate base of a weak acid. This is going to be a basic solution. A little bit of a hint on that would be right here. You can see that you have the OH coming off. So it is going to be weak. Okay, then if we're going to take a look at an acid solution, let's see, where do I have that? All right, I have a strong conjugate acid of a weak base will form acidic solutions. Okay, sorry, someone came in here and I had to stop for a second. That's why I wasn't really fully paying attention. So if we take a look, this time our solution is going to be ammonium chloride. We have used this many times back in lab. And so if this is going to be my solution, ammonium chloride, take it apart, what are my species? So my species are going to be the ammonium ion. I'm going to have my chloride ion, and I'm still going to have water. So these are all the species that are involved in this. So if I take a look, it says I have a salt again. Well, which one of these is not going to form anything? If I take a look, we talked about above, that's the chlorine ion right up here, that these are not going to have any effect on my pH because they are weak conjugate bases from a strong acid. So that chloride ion is not going to do anything, so it's going to be a spectator ion. It's not going to affect my pH. So then I have my ammonium ion plus water, and in this situation, I'm going to get ammonia with no excess charge there, plus my hydronium ion. So then, again, I can see that I have my hydronium ion, which signifies of an acid, so I know that I have an acid solution. So the biggest point of this, you guys, is to make sure that you understand that there are spectator ions again, and especially we're going back again where we're talking about salts. Okay, so we are done with this section, 14.7 and 14.6, sorry, and 14.7. I hope you guys have an awesome day, and I will see you soon.